Hello, so let's do a couple more questions. Let's get a few done. Okay, so a question like this. Some people insist on using product rule. I really am against that, even though my old maths teacher used to do exactly that. The reason I'm against it is because it's easier to simplify with quotient rule, and you get quotient rule in the formula book. So let's use quotient rule. Now, quotient rule, I just remember the little rhyme, low d high minus high d low over the square of what's below. So what we need to do if we're differentiating this with respect to theta, please don't write x, that will annoy me, is do low but differentiate the high. So low, differentiate high, cos 2 theta differentiates to minus 2 sine 2 theta, minus high, well, that's cos 2 theta. Put it in brackets if you like, because it's going to be pretty messy. D low. Now the bottom differentiate, sine 2 theta differentiate to 2 cos 2 theta. So I'm going to put the 2 there and the cos 2 theta here. Oh, and there's some lovely looking things in that. Over the square of what's below. So 1 plus sine 2 theta squared. Okay, you get like, 1 mark for doing that correctly, maybe even 2, it depends. Okay, that leaves us with minus 2 when we expand those brackets, sine 2 theta. Sorry, I almost forgot about the sine 2 theta on the end there. Be careful with that. Minus 2 sine squared 2 theta. And then minus 2 cos squared 2 theta. Now, I'm really happy with that the last two terms in that, because actually that's going to simplify nicely, because what you can do, sine 2 theta, try and make your 2's and your squares clearly different, because obviously in this kind of question where you've got lots of squares and 2's, and double arguments, it's really easy to get confused. So make sure your handwriting isn't awful, Christian. Okay, minus 2 sine 2 theta. Minus 2. Let's factorize out the minus 2 and it'll be more obvious to you. And then we've got sine squared 2 theta plus cos squared 2 theta. Well, sine squared of stuff plus cos squared of stuff. Yeah, it doesn't matter what the stuff is, as long as it's the same stuff. It always is identical with 1. Yeah, that's essentially what we're going to use in the next step. So that is actually just going to become 1 over 1 plus sine 2 theta squared. Yeah, people will not like this question in exams, I'm sure, because that leaves you with minus 2 sine 2 theta minus 2, because it's just 1 over 1 plus sine 2 theta squared. Factorize out the minus 2 once again, and you've got 1 plus sine 2 theta, which is what you've got squared on the bottom. And so it starts to become obvious that A is in fact going to be minus 2 over 1 plus sine 2 theta, as they said it would be. And that's that question done. Hope that makes sense. Okay, should we scroll down and do the next question? I think we should. Let me get rid of that. I think I've finally worked out how to get rid of it. There we go. Let's do number 4 as well. Let's just go straight into it. Okay, so what have we got here? A little bit of integration, I love a bit of integration. Now, you can learn this formula, a plus bx, if you're a formula junkie, and some students are. A plus bx to the m with respect to x always, always, always integrates to a plus bx to the m plus 1 over b times m plus 1. Yeah, you can learn that formula, and often students like to learn formula. So by all means, sometimes it's described as reverse chain rule as well, which essentially it is. But let's say you don't like the formula approach. Let's say you want to use a bit of substitution. Good for you. Let's quickly prove that it integrates to what it does by substitution. We've got to the power of 12 dx. Let's let u equal 2x plus 3. Then du by dx is 2, or in other words, du is swappable with 2 dx. But another way of looking at that is a half du is dx, yeah? I like looking at it like that, because then what I can say is, when I've got a dx, I can trade that for a half du, so the dx has become a half du, and then I've got u to the power of 12. Well, that's going to integrate to a half u to the power of 13 over 13. Increase the power by 1, divide by the new power. And so it is, in fact, plus a constant c. Let's put the plus c on, or plus k, I'll call it today. U now we can swap back for 2x plus 3 to the power of 13 over 26 plus k, yeah? And note, my first formula would have given exactly the same answer. You would have had, I've written it as a plus bx. Maybe I should have written it as ax plus b. It would have been clearer what's going on there. But can you see we needed to divide by the 2 times by 13, which is 26. Okay, part B, another classic kind of integration, not anything weird going on here. We've got to integrate 5x over 4x squared plus 1. Now, one nifty little trick with integration is always, if the bottom differentiates to the top, then it integrates to natural log of the bottom. Now, it looks like it might be similar to that, but it doesn't quite differentiate to 5x, does it? It differentiates to 8x. And my approach to these ones is cheat. Yeah, so let's just draw an 8x on the top. Now that's a bit cheeky, isn't it? You can't just change 5x to 8x. That's just completely wrong. So what do we have to times 8x by to make 5x? Well, we need to surely times 8x by 5/8. Yeah? So I can just sneak that on the top, and then that is the same as the line of working above it. That is absolutely the same as that. Well, what I can do now is I can chuck any constants of integration outside the integral. So this becomes integrate 5/8 of 8x over 4x squared plus 1 with respect to x. And that now I can use the log principle that when the bottom differentiates to the top, the answer is natural log of the bottom. Technically speaking, I really need this in a modulus because it's a natural logarithm, but they're not going to worry too much about that. And then we've got a plus a constant on the end, which I'll call c this time. Okay, I hope both of those made sense. Well done.